Hello friends, welcome back to our channel Abhi Chemistry Tutorial. So in this video we are going to discuss some repeated questions of inorganic chemistry which are asked for previous set examinations. So before going into the video, if you have not subscribed it, please take a second to subscribe and kindly support me and share this video to your friends and watch till end so that you will be benefited for your CSIR NET and set preparations. So the first question is the correct order of ionic radii is given by. So there are four ions are given. So I will give you a small trick for answering this question. So if the ion is having negative charge, then the ionic radius will be high. Okay, if the ion is having negative charge, the ionic radius will be high, and if the ion is having positive charge, the ionic radius will be less, and if it is neutral, it will be in between. So here we have four ions. So if we are having a single negative charge, the radius will be high. So if you are having more negative charge like 2 minus 3 minus, then it will be the ionic radius will be high. Similarly, if there is plus charge, it will be small in size, and if it is again 2 plus or 3 plus, the ionic radii will decrease. So keeping this trick in mind, if you are solving these four ions, S2 minus will have the radius, bigger radius, and then Cl minus, and then K plus, and 2 plus, calcium 2 plus will have a very small size because of its positive charge. Okay, so the answer is option B. Second question, the second ionization energies of lithium, beryllium, boron and carbon are in the order. Okay, so first we will calculate the first ionization energy. So we know a general trend that in periodic table, when we move from left to right, the ionization energy will increase. So after removing one electron, I have written the electronic configurations here. So after removing 2s1, the electronic configuration for lithium will be 1s2. For beryllium, it will be 1s2, 2s1, and for boron, it will be 1s2, 2s2, and 2p0 after removing this one. And here, after removing 2p1, 2p2, 1 electron, there will be 2p1 electron. And for second ionization energy, we have to remove 1 electron from all these outer orbitals. So here you can see 1s orbital is tightly bound to the nucleus. So it is very difficult to remove electron from 1s orbital. So this will have higher ionization energy. And next you can see here boron also, here we have 2s2, so it is also completely filled, so boron will have the next second ionization energy. And then coming to this carbon is having 2p1 above this 2s2 orbital, so it will be again difficult. And then comes the beryllium. So order of second ionization energy is lithium, boron, carbon and beryllium. Among the following, which has the maximum hydration energy? Third question. So four options are given. So hydration enthalpy will be directly proportional to charge or charge density and inversely proportional to radius. So there is a general trend regarding this. So consider group 1 and group 2 elements. Ions, consider them as ions. The first group will have plus charge and the second group will have 2 plus, okay, plus 1 and here 2 plus. So down the group, the ion becomes larger, that is the size or radius increases, so which means hydration enthalpy will decrease, and also charge density will decrease down the group, so that the hydration enthalpy will decrease down the group. And in the case of period, from group 1 to group 2, if you are seeing, the charge will increase. Okay, so plus 1 to plus 2, the charge will increase, so the hydration enthalpy will also increase. And also in the group, in the period, the size of the ions will decrease, so the radius will decrease, so the hydration enthalpy will increase. So in general, comparing group 1 and group 2 ions, the group 2 ions will have higher hydration enthalpy than the group 1 ions. So keeping this in mind, we can reject option A and B since they are group 1 elements. So here C and D. So here we have to apply the trend of group. Okay. So down the group the charge density decreases, or down the group the size increases. So size increases. So for comparing magnesium and calcium, calcium is bigger in size than magnesium. So magnesium has lower size than calcium. So magnesium has lower size, so hydration enthalpy will be high compared to that of calcium. So the answer is magnesium 2+. And the fourth question is arranged in the order of increasing dipole moment. So BF3, H2S and H2O. So BF3, this is the structure of BF3. So there will be a net dipole moment of these two fluorine, and this will be cancelled by the dipole moment on the other side. This is non-polar, and H2S and H2O are both are polar components, but the electronegativity difference between oxygen and hydrogen is more compared to that of sulfur and hydrogen. So water is more polar than H2S, and so the dipole moment of water is very high than that of H2S and than that of BF3. So the next question is the angle between three iodine atoms of I3 minus ion is. So I minus, there are total of, in case of just iodine, when it is involved in covalent bond, there are 7 electrons in the outer shell. And it is I minus, so 1 more electron. So 7 plus 1, it is 8 electron. So now 8 electrons are shared between these other two iodine atoms. So here you can see 1, 2 and 3, 4, 5, 6, 7, 8. Okay. So 2 lone pairs on one side and 1 lone pair on the other side. And these two iodines are linear in structure in the straight line. So the structure is linear, and the degree and the angle between these 3 iodine atoms is 180 degree. Okay. So other informations about this I3 minus is number of lone pairs. So 1, 2, 3. Similarly, these iodine will also have 1, 2, 3, 4, 5, 6, 7. So 3 lone pairs. So 3, 3, 3, 3 plus 3 plus 3, 9 lone pairs. Geometry. So this is nearly equal to this trigonal bipyramidal geometry. Yeah. Here 2 set of lone pairs, 1 set of lone pair here, and here iodine and iodine. So the geometry is trigonal bipyramidal, and hybridization is sp3d. Sixth question is match the following class of boranes with the examples. So before connecting the classes with the formula, there are some types of boranes which are represented by general representation. Okay, so closo, nido, arachno, hypo, clado boranes. So closo boranes means BnHn2 minus. Nido boranes means BnHn4 minus. Arachnoborane means BnHn6 minus. And hypoborane means BnHn8 minus. Cladoborane means BnHn10 minus. So these are the types of boranes. So here we can see B8H14. So B8H8. Now we have 2 minus 14 minus 8, which is 6. So B8H8 6 minus. So BnHn 6 minus belongs to arachnoborane. So answer is arachnoborane. Next one is B10H10 2 minus. So BnHn 2 minus, which is closoborane. So the answer is closoborane. B9H13. B9H9. So 13 minus 9, which is 4. So 4 minus. Okay. So 4 minus belongs to nidoborane. Okay, nidoborane. And the seventh question is in B2H6 each boron atom is hybridized as. What is the hybridization of boron in diborane? So diborane B2H6, and here you can see this boron and boron is bonded through hydrogen by a 3-center 2-electron bond, that is banana bond, and but still this each borane is connected to 4 bonds, connected to 4 different hydrogens through 4 bonds. So this represents that both the boron atoms are having sp3 hybridization. So additional informations, the angle between this HBH is 97 degree and BHB is 83 degree, and the diborane has 4 terminal hydrogen atoms and 2 bridging hydrogen atoms, and there are 2 3 center 2 electron bonds and 4 2 center 2 electron bonds. The next question is tetragonal distortion, distorted complexes will be exhibited by. So 4 options are given. Tetragonal distortion means Jahn-Teller distortion, which is equivalent to unsymmetrical T2G or EG orbital. So we are writing the distribution of energy levels for all the 4 options. So low spin Fe2 plus means 3d6. There is no possibility of Jahn-Teller distortion. In chromium 2 plus 3d4 high spin, there is unsymmetrical T2G EG orbital. So there is a possibility for Jahn-Teller distortion. We will see the other options also. Mn2 plus, that is 3d5 in high spin. So there also there is no Jahn-Teller distortion. And Ni2 plus, that is 3d8. Here also there is no chance of Jahn-Teller distortion. So only the option B is possible for Jahn-Teller distortion. So the answer is option B, high spin Cr2 plus. Ninth question, the coordination number and geometry of cerium in cerium NO3 are respectively. So 4 options are given. For lanthanides, usually the coordination number is more than 6 and high spin orbit coupling is present and larger in size. So here in this compound, the cerium is bonded to 6 NO3 groups. So each NO3 group is bonded to cerium like this, N double bond O, 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 and both the oxygen atoms are linked to cerium. So each NO3 group behaves like a bidentate ligand. So bidentate, 2 into 6 ligands. The coordination number becomes 12 and the geometry is icosahedral geometry. So what is icosahedral geometry? It is a 3D shape with 20 equilateral triangle faces and the cerium atom at its center. So I will attach this structure of cerium NO3 image for your reference. So the answer is option D, 12 and icosahedral. So 10th question. The number of possible isomers for ruthenium bipyridine 2 Cl2 is. So this I have discussed in a video in which I have explained isomerism in tetrahedral octahedral complexes, where I explained to calculate number of stereoisomers. So here also this that is the same question here but different complex. So bipyridine is a chelating ligand. So this is the cis structure and this is the trans structure. So 2 geometrical isomers are possible and it is optically active. So when it is optically active, plus and minus isomers are possible. So 2 isomers are possible. So here you can see we get 2 non-superimposable mirror images. So number of stereoisomers can be calculated using the formula geometrical isomers plus half into optical isomers. So geometrical isomers are 2 plus half into optical isomers are also again 2. So the answer is total number of isomers possible is 3. 11th question is hexaaqua manganese 2 high spin complex consists of 4 electronic transitions. So among these 4 electronic transitions, which are Laporte allowed and spin allowed? So that is the question. So this is the complex hexaaqua manganese 2 plus, and since it is high spin, 3d5 is written like this. So the transition must be DD transition. So DD transition is always Laporte forbidden. And here you can see all the T2G and EG levels are filled with only one spin type, that is either clockwise. If you consider it as clockwise, it is clockwise spin. So it should be of opposite spin, for it should be spin allowed. So both are having the same spin. Both levels are having the same spin. So it is spin forbidden. The transitions are spin forbidden. Coming to the selection rule, Laporte and spin transitions are there. So Laporte, if it should be Laporte allowed, then it should be delta L is equal to plus or minus 1. This is the selection rule. And for spin allowed transitions, the selection rule is delta S equal to 0. So there should be change in parity in case of Laporte allowed transitions. That is, it should be from S to P or P to D or D to F. And it should not be D to D or P to P or S to S. It is Laporte forbidden. So you know L is 0, 1, 2, 3. If it is 0, it is S, 1 is P, 2 is D, and 3 is F. Okay. So spin also, in case of spin allowed transitions, delta S should be 0. That is both the levels should have +1 and -1 spin electrons, not +1 or -1. Okay. So this is the selection rule as per Laporte selection rule and spin selection rule. So the next question, the ligand field bands of lanthanide complexes are generally sharper than that of transition metal complexes. Why? So lanthanides are f orbitals and transition metals have d orbitals. Okay, so comparing to d and f orbitals, 4 orbitals are deeply buried. Okay, so the interaction of ligands with f orbitals is less effective than with the d orbitals because 4 f orbitals are deeply buried. So the fact is that the ligand interacts less with 4 f orbitals, so it produces sharp band, and when in case of d orbitals the interaction is more, so it produces broadened band. So the ligand cannot interact well with the f orbital and they give sharp band, and if the ligand interact well with the f orbital they give broad band. The next question given below are two statements. Statement 1, zirconium and hafnium occur together in nature and their separation is difficult. Statement 2, they have similar size due to lanthanide contraction. So zirconium and hafnium, they are said to be chemical twins because of lanthanide contraction. So the separation of zirconium and hafnium is difficult. So that statement 1 is true. And statement 2, they have similar size due to lanthanide contraction. That is also true because the f orbital or f subshell is having very poor shielding effect. So the nucleus will attract the electrons strongly, and thus the size of hafnium will be reduced and it becomes almost similar to that of zirconium. So both are having almost similar sizes. So the atomic radii of zirconium is 1.45 Armstrong and that of hafnium is 1.44 Armstrong, which is almost similar. Okay, or almost the same we can say. So the statement 1 and 2 are correct, and 2 is the correct explanation for statement 1. The 14th question is the correct order of strength of metal carbon bond in the given carboxyls is. Okay, so 3 carboxyl groups or complexes are given, one with a negative charge, one is neutral and one is positive. And now we have to find the strength. Which complex is having more metal carbon strength? Okay, so the frequency is directly proportional to strength. So the frequency of metal carbon bond is directly proportional to back bonding and it is directly proportional to electron density. So if back bonding increases, frequency will increase and so the strength will be high. If electron density is high, the back bonding is high and the strength is also high. In case of metal carbon, so it will be the reverse for carbon oxygen. Okay, so the back bonding is explained here. So carbon oxygen will have a triple bond, so one of these bond will come back towards this metal carbon and the structure will be modified like this. So this is back bonding. So if the frequency of metal carbon increases, at the same time the frequency of carbon oxygen bond or the strength of carbon oxygen bond will decrease. Since there are 3 bonds which is reduced to double bond, no? So the frequency or the strength will decrease. Okay, electron density is directly proportional to back bonding. So if you are calculating using electron density, negative charge means the electron density is high. So if the electron density is high, the frequency is more and the strength is also more. So VCO6 minus, which is having negative charge, will have more strength of metal carbon, and next positive charge will have less electron density. So in our case manganese CO6 plus will have less strength. So the neutral electron density will be in between positive and negative. So the order of strength will be VCO6 minus and then the neutral complex and then the positive charged one. So if it is asked for carbon oxygen bond, then the order should be reversed. So manganese MnCO6 plus will be high, then CrCO6 and vanadium CO6 at last. or the least strength compound will be the negative charged one. 15th question, the transformation of oxyhemoglobin to deoxyhemoglobin. So hemoglobin, the main central metal atom is Fe2 plus in the porphyrin ring. So in case of if oxygen is present, the Fe2 plus will be in low spin state, and if there is no oxygen, then the Fe2 plus ion will be in the high spin state, but the oxidation state will remain constant. So the answer is Fe2 plus in low spin state changes to Fe2 plus in high spin state when oxyhemoglobin is converted to deoxyhemoglobin. So in oxyhemoglobin, Fe2 plus in low spin state, and in case of deoxyhemoglobin, Fe2 plus in high spin state. The last question, the copper containing protein involved in the oxygen transport is option A cytochrome C, option B hemerythrin, C hemocyanin, and D myoglobin. So cytochrome C contains iron, hemerythrin contains iron, hemocyanin contains copper, myoglobin contains iron. So the question is copper containing protein. So the answer is option C hemocyanin, which contains copper. So I think this revision or these repeated questions series is more helpful for you. So if you like the video, please put a thumbs up and share to your friends, and don't forget to subscribe to our channel and click the bell button so that you will be notified whenever I upload a new video. So stay tuned. I have uploaded many other videos in our channel, so kindly check all those videos. See you on the next video. Until then, bye. Thank you. Take care.